If the molar solubility of calcium fluoride at 35 degrees Celsius is 1.24 times 10 to the minus 3 moles per liter, what is KSP at this temperature? All right. Molar solubility is how many moles per liter of the solid goes into solution. So that's going to be reflected in the calcium ion concentration. For every 1 mole of calcium fluoride, you're getting 1 mole of calcium ion. So for every 1.2 times 10 to the minus 4 molar calcium fluoride going in, that's the calcium concentration. The fluoride concentration is going to be twice the molar solubility, right? You're getting 2 times the fluoride ion compared to the 1 mole of calcium fluoride. So you take these concentrations, plug them into the law of mass action, right? So it's going to be the concentration of the fluoride raised to the second power times the concentration of the calcium raised to the first power, and that's going to be equal to the KSP. C, going the other way. I know what the KSP value is. It's cut off there because I chopped out question B. But it's 6 times 10 to the minus 10. So this is a very insoluble ionic compound. For every 1 mole of barium iodate, you're getting 2 moles of iodate and 1 mole of barium. So when you break apart barium iodate, you're getting X amount of barium ion, 2X amount of iodate ion. So these are the equilibrium concentrations. You plug these concentrations into the law of mass action. The iodate concentration raised to the second power. Barium concentration raised to the first power. So 2x squared is 4x squared times x is 4x cubed. All right, so that's how you work this. The squared is outside the bracket, so it's 4x squared times x is 4x cubed. So divide both sides by 4, take the cube root of both sides, and you get x, which is the molar solubility. So that's how you do these problems. A 1 liter solution of saturated, a 1 liter solution saturated at 25 degrees Celsius with calcium oxalate contains 0.0061 grams. Calculate the solubility product for the salt. So you've got to get it in moles per liter. Use the molar mass of calcium oxalate to convert to moles, divide by liters to get the molarity. The molarity is going to represent the concentration of each ion, right? The molar. So this is the concentration of each ion, right? 1 mole of calcium oxalate breaks up into 1 mole of calcium, 1 mole of oxalate. So take these concentrations, plug them into the law of mass action, and solve for KSP. Use Appendix D to calculate the molar solubility of silver bromide in pure water. In pure water, for every X amount of silver bromide lost, you're making X amount of silver ion, X amount of bromide. These are the equilibrium concentrations. Plug them into the law of mass action, set them equal to the KSP value, and solve for X. That represents the molar solubility in pure water. B, in 3 times 10 to the minus 2 molar silver nitrate. So what we're introducing here is a common ion. Common ion is going to suppress the solubility of this ionic compound, right? It's going to shift it back towards the solid. So X is going to be smaller. So plug these concentrations into the law of mass action, right? I mean, the amount of silver you're making here is going to be inconsequential. So just take the concentration that you're given of silver, plug it in, and solve for X. The bromide ion concentration will represent the molar solubility of the solid. C, 0.1 molar sodium bromide. So this time we've got the other ion acting as the common ion. So solve for X. Take these equilibrium concentrations, plug them into the law of mass action, solve for X, and get the molar solubility with bromide ion, suppressing the solubility of silver bromide. Consider a beaker containing a saturated solution of calcium fluoride in equilibrium with undissolved calcium fluoride. If solid calcium chloride is added to the solution, will the amount of calcium fluoride solid at the bottom of the beaker increase, decrease, or remain the same? Well, calcium ion is a common ion here. So as I increase the concentration of the calcium ion, I'm going to shift the equilibrium back towards the solid and increase the solid and decrease the fluoride concentration. So as the calcium ions increase, they find more of the fluoride ions to react with and trap them in the solid. So as the calcium ion concentration goes up, the fluoride concentration goes down, and it drives the equilibrium towards the solid side. Will the calcium ion concentration solution increase or decrease? Well, they'll, will the concentration of the calcium ions in the solution increase or decrease? Well, they'll increase, right? So as you add the calcium chloride. Chloride's a spectator ion here, and as the calcium concentration goes up, the fluoride concentration goes down. Which of the following salts will be substantially more soluble in an acidic solution than pure water? All right, so what we're looking for here is conjugate bases of weak acids. So that's carbonate. So if I put acid in this solution, acid is going to take this carbonate out of this equilibrium and shift it towards the product side, right? So as the carbonate concentration goes down, the solubility of zinc carbonate increases, as shown by the increasing zinc concentration. Same with zinc sulfide. Sulfide is the conjugate base of hydrosulfuric acid. So as I put H plus into this solution, it's going to eat up the sulfide and drive this solid forward and increase its solubility. Not so with bismuth iodide. Iodide is the conjugate of hydroiodic acid, which is strong acid. So putting H in here isn't going to do a thing, right? Iodide is a miserable base, and it's not going to react with the H plus ion. Silver cyanide will, though. Cyanide is the conjugate base of hydrocyanic acid. Putting H plus ion in here will take it out of this equilibrium, shifting it forward towards the products, increasing the silver concentration as the cyanide concentration goes down.